Okay, class, we just discussed percent composition by mass for compounds as another way of presenting the composition of molecules. It's a little bit of a cumbersome way, but the reason we present it is that sometimes experimentally one would perform a combustion analysis of a compound in order to determine the components, the elemental components of a molecule, and so we had to define what we mean by percent composition. So let's talk about a combustion analysis. And imagine that you're working in the laboratory of Avi Susho at NCIS, and you're given a sample of some unknown material, and you want to determine how much of particular elements are in this compound so that you might be able to determine the molecular formula. So you perform a combustion analysis, which, as the name implies, you heat it up, you burn it in the presence of air, and doing so converts any carbon in that molecule to carbon dioxide, any sulfur in that molecule to sulfur dioxide, any nitrogen to nitrogen dioxide, and any hydrogens to water, as shown in the equations below. So if you can then collect the carbon dioxide, sulfur dioxide, nitrogen dioxide, or water that is formed as a result of this combustion process, weigh that amount of those gases formed, you can then, by dividing by the molar mass or molecular weight of carbon dioxide, sulfur dioxide, etc., determine the number of moles of carbon dioxide produced, likewise sulfur dioxide, etc., and then relate that back to the number of moles of carbon, sulfur, nitrogen, etc., in the starting material. The key is that there's a one-to-one stoichiometric relationship between the number of moles of carbon in the sample and the number of moles of carbon dioxide produced. So if you can determine the latter, you can get the former. The only one that's different is water. If you notice the reaction, it takes 2 hydrogens in the sample to produce 1 mole of water vapor. So if you collect water vapor and weigh it and divide by the molar mass of water, 18 grams per mole, to get the number of moles of water formed, there must have been twice as many moles of hydrogen in the original sample. So that's the only one that's a little bit different that you have to be aware of. Now I'm going to give you 2 example problems, one in which the compound contains only carbon and hydrogen. That's a relatively straightforward problem. And then the second problem will be one in which the compound contained carbon, hydrogen, and also oxygen. Now, to determine the composition of oxygen in the molecule, you have to do this by difference because we can't burn oxygen in the presence of oxygen to prepare oxygen because oxygen is there. It's the reactant. So to determine the oxygens in a molecule, we have to determine everything else, and then by difference, whatever is left over must have been oxygen. So the first example, we're given a compound that we're told it contains only carbon and hydrogen, thank you very much, and we perform a combustion analysis yielding, or we collect, 1.83 grams of carbon dioxide and 0.901 grams of water vapor. So, as we said, we take the number of grams of oxygen, divide by the molar mass of carbon dioxide, which happens to be 44, to get the number of moles of carbon dioxide produced in the combustion analysis, 0.0416 moles, and we rationalize that there must have been the same number of moles of carbon in that sample that we burned. Similarly, if we produce 0.901 grams of water vapor, we divide by 18 grams per mole, the molecular weight of water, to get 0.05 moles of water that was produced. And we rationalize, remember, we have to be aware of this one, we rationalize that there must have been twice as many moles of hydrogen in the starting molecule, or 0.10 moles. Now, to then determine the empirical formula, we divide by the smallest number of moles. This is a trick you'll learn, and we'll do this quite often. So we divide both numbers by 0.0416, the smallest number of moles. Of course, dividing that number by itself gives you 1, but dividing 0.10 by 0.0416 gives us 2.4 as a relative number of hydrogen atoms in the molecule. So we get the ratio of 2.4 hydrogens to 1.0 carbons in this molecule, and that is the empirical formula. But we're not quite satisfied because we can't have 2.4 hydrogen in a molecule. It must be whole numbers. So we have to think of what whole number can we multiply both 1 and 2.4 by to convert both to whole numbers. And if we think about it a little bit, that number will be 5. So if we multiply C1 H2.4 by 5, we get C5H12. that is, both elements as whole numbers. And this would then be the more correct empirical formula. Now, this may or may not be the molecular formula, but if we were told, if someone did a separate experiment and told us that the molecular weight of this compound is 72, we would say, okay, then C5H12 is also the molecular formula. That's because the molecular weight of a compound C5H12 would be 5 times 12 for carbon, 60 plus 12, it would be 72. Okay, so this was the first example of a combustion analysis. Now let's go to a second example in which the compound contains oxygen. In this case, we have to know the initial weight, the initial mass of the sample which was subjected to a combustion analysis. So we're told in this example it's 0.8233 grams of the sample. We burn in the presence of oxygen, we yield 2.445 grams of carbon dioxide and 0.6003 grams of water. So we perform the steps as we did before by taking that mass of carbon dioxide, dividing by 44 to get the number of moles of carbon dioxide, 0.05556 moles of carbon dioxide in the sample. Therefore, there must be the same number of moles of carbon in the sample. And secondly, we take 0.6003 grams of water, divided by 18 grams per mole for water to get 0.0331 moles of water that was produced, and there must then be twice as many moles of hydrogen in the compound. That's 0.06662. So that's the number of moles of carbon and hydrogen, but we were told that the molecule also contains oxygen. So how do we get that? Well, we have to determine the mass that was oxygen. We do this by subtracting the mass that we just determined to be for carbon and the mass that is for hydrogen. How do we do that? Well, we take that number of moles of carbon that we just determined, 0.05556 mole, multiplied by 12 grams per mole to get 0.6673 grams of carbon that must have been in the sample. Likewise, the number of moles we determined for hydrogen, 0.06662, we multiply that by the molar mass of a hydrogen atom, 1 gram per mole to get, that's an easy multiplication step, 0.0667 grams of hydrogen in the sample. We add those two together to get the mass that must have been for carbon plus oxygen in the sample, 0.7340. Now, that mass is less than the mass of the sample that we started with. Thankfully, that means we've done our math correctly. But if we subtract that 0.7340 grams from the mass of the sample that we started with, 0.8233 grams, we get the mass of 0.0893 grams, which must have been oxygen in the sample. If we then divide that mass by 16, the molar mass of an oxygen atom, we can then determine the number of moles of oxygen in the sample. We already above determined the number of moles of carbon and the number of moles of hydrogen. And we then play the trick again of dividing by the smallest number of moles to get the relative number of each element in the compound. When we do this, we would find an empirical formula of C10H12O1. So this is a fairly complicated problem. This is a combustion analysis in which oxygen is present in the molecule. Try to practice a few of these from the homework. Now next I want to talk about hydrates because they're similar type of problems to combustion analyses. Some ionic compounds exist as what we call hydrates, solid hydrates. They're solids, but we sometimes say they're wet because they've absorbed one or more water molecules into the solid. A classical example of that is copper sulfate with 5 waters, which is represented here. It turns out that the hydrated form is a blue crystal, as shown to the left. If we were to remove all of the water molecules, which we can do by heating in a vacuum oven, essentially evaporating away the water molecules, the copper sulfate in its anhydrous form is actually a white or a grayish-white solid. The reaction shown is basically that for the heating and removal of water from copper pentahydrate. What if we don't know the number of water molecules in a hydrate? In the above example, it was 5, but what if we have a sample of another hydrate, such as nickel 2 sulfate, with X unknown number of water molecules as a hydrate? Could we determine X? Yes, we could. If we were to take a sample, such as a 10-gram sample of this nickel sulfate hydrate, heat it in an oven to drive off the water vapor, and what if we were to find that there were 5.89 grams of anhydrous nickel sulfate left behind? We could then use this to determine the value of X for the hydrate. Well, how? Well, we take the 5.89 grams of nickel sulfate, divide by the molar mass of nickel sulfate, which happens to be 154.7. I'll give it to you, but you could quickly add that up by taking the molar mass of nickel, molar mass of sulfate, and 4 molar masses of oxygen, adding that up, and you get 154.7. If you divide the residual 5.89 grams of nickel sulfate by 154.7 grams, you would get 0.038 moles of nickel sulfate. The mass that was driven off by difference would have been 4.11 grams of water. If you then divide that by 18 grams per mole, you'd get 0.228 moles of water. Again, as we've done before, you divide both of these number of moles by the smallest number, the number for the number of moles of nickel sulfate, and you'd get the value of X. In this case, that we'd find that X is 6, and so this would be a nickel, Roman numeral 2, sulfate, hexa for 6, hexahydrate. So hydrates and problems that are similar to combustion analyses. Now in the last slide in this chapter, I want to talk about balancing equations. Oftentimes you worry that this is difficult. No, this is easier than you think. And in fact, if you do the complicated ones, such as I'm going to show here, then the others will be like rolling off a log. The more complicated ones are ones that have a particular element, in this case it would be oxygen, appearing in 2 or more molecules on one or the other side of a chemical reaction. What I just said sounded complicated, didn't it? But if you look at this reaction, I have C4H10 in the gaseous phase plus oxygen going to carbon dioxide plus water. So this is a reaction that's unbalanced, as you can see, and the question is, how do we balance it? And the reason I said it's complicated, or slightly complicated, just slightly, is that oxygen appears in 2 different molecules on the product side. It appears in carbon dioxide and appears in water. So here's the advice. When balancing these reactions, leave that element that appears in multiple places, leave it to last when you try to do the balancing. And I'll show you what I mean here. So if you start with the first thing you see, and I always tell students, start with the first thing you see, and the first thing you see is the carbon on the left, carbon, and you see that there are 4 of them on the reactant side. If you look to the product side, the only place you see carbon is in carbon dioxide, and so you must place a 4 in front of the carbon dioxide. Okay, and all right, going so far. And then you go back to the left and you say the second thing you see. The second thing you see is hydrogen, and there are 10 of them on the left hand or the reactant side. You look to the product side, and hydrogen appears only one place. In water, it's H2O, so you must place a 5. 5 times 2 would be 10. Must place a 5 in front of the water. So you've now balanced this reaction for both the carbon and the hydrogen. We leave to last the complicating element, that's oxygen. If you look on the left, oxygen appears as O2. If you look on the right, it appears twice in 2 different molecules. We now have 4 CO2, so we have 8 oxygens in carbon dioxide, 4 times 2, 8, plus the 5 for the 5 waters. 8 plus 5 is 13. So that means that we need to have 13 oxygens on the reactant side, but it's O2, so that means we need to have 6.5 O2s, 6.5 diatomic oxygens. So this reaction is actually now balanced for carbon, hydrogen, and oxygen. But we may not be satisfied by having fractions, and so if we want, we can multiply everything by 2 to get rid of that fraction, get rid of the 6 halves, and that would be as shown here. 2 C4H10s, which is actually something called butane, plus 13 oxygens goes to 8 carbon dioxides and 10 waters. Now you see the balanced reaction looks a little complicated, but if you follow these steps, it actually turns out to be rather easy. Okay, so we'll stop now. So we've now finished the chapter on molecules and compounds.